Hi folks, we're going to take a look at page 61, number 19. So in this question here, they give us two vectors A and B, and they tell us that these vectors are the diagonals of a parallelogram. Okay, and what they want us to do is show that it's a rhombus, so that means all four sides should be equal, and then find the length of those sides, so it really should only be one length, and then the angle between the sides. Okay, and if you think in a parallelogram, once you know one of the angles, you're able to find all the other angles. Okay, so first thing I'm going to do here is I'm going to rewrite this in algebraic form. It'll be a lot easier to work with. So here this will be the vector 3, -4, -1, and this will be the vector 2, 3, -6. Okay, and I'm going to draw myself a picture here to help me out. So I've got some sort of parallelogram. And the vectors they're giving me here are actually the vectors of the diagonal. There's one vector, and there's another vector. Okay. Now, one thing I want you to remember is that the diagonals of a parallelogram have a meaning if you think of these adjacent side lengths as being two vectors. Okay. We know that the this diagonal here that starts from the two tails of the vector is going to be the sum of those two vectors, and then the other diagonal will be the difference between those two vectors. Now notice here, this is just a diagram to help me determine how to proceed in this problem. I could have taken this as my vector, say u, and that my vector v, then that would have been the sum, that would have been the difference. So it doesn't matter how I draw it, as long as I'm applying the relationships between these sides correctly. Okay, so let's call this a vector u, and let's call this vector v, just give them a name, and I'll call this first diagonal the vector a, which I'm given, and then this second diagonal here will be the other diagonal. Okay, so if I add these two vectors together, I should get one of the diagonals. Okay, so let's add them together. So when I say these two vectors, u and v, so what I'll do is I'll call u x1, y1, z1. Okay, and I'll call v x2, y2, z2. Okay, so if I add these two vectors together, I'll get vector a, and if I subtract them, I'll get vector v. So what happens when I add these two vectors together? Well, I have x1 plus x2, y1 plus y2, and then z1 plus z2. Okay, and this vector here should be equal to what I'm designating as the sum, 3, -4, -1. Then if I subtract the two vectors, so if I do x1 minus x2, y1 minus y2, z1 minus z2, okay, I'm going to designate that as the difference between the two vectors. Okay, 2, 3, -6. Okay, so I now have these two vectors here, but I notice that in each of the components, I've got two variables in each component. Normally that would be a problem, but since I also have this second relationship, these components have the same two variables as the previous one. So two variables, you should be thinking solving a system of equations, and that's exactly what we can do. So I'm going to solve a system of equations for the x component, the y component, and the z components. Okay, so if I take that first one, I have x1 plus x2 equals 3, and I've got x1 minus x2 equals 2. Okay, subtract, or actually let me add them. We'll get rid of the x2's, and what do we have? We have 2x1 equals 3 plus 2 is 5, so x1 is equal to 2.5. Okay, and now we can find x2, so x2 is just going to be, let's take that first one, 3, bring the x1 to the other side, minus 2.5, so that's equal to 0.5. So we have the two x components. Now I'll do the same thing with the y components, so y1 plus y2 is equal to -4, and y1 minus y2 is equal to 3. Okay, and again, let's add them here. So we got 2y1 is equal to, these cancel out, negative 4 plus 3 is negative 1. So y1 is negative 0.5, and y2, okay, if I use that one there, I have negative 4 minus y1, which is negative 0.5. So negative 4 plus 0.5 is equal to negative 3.5. Okay, and lastly, let's do that for the z components. z1 plus z2 equals negative 1, and z1 minus z2 is equal to negative 6. So again, I'm going to add these together. So I get 2z1 is equal to negative 1 minus 6 is negative 7, and then z1 is equal to negative 3.5, and z2, if I take this equation here, will be negative 1. Okay, and then let's take the negative 0.5 to this, so I'm going to subtract the negative 3.5, and what do we have? Negative 1 plus 3.5 is 2.5. Okay, so now I know my two vectors u and v, which I put together to create the parallelogram. Okay, are u is going to be x1, x2, x1, y1, z1. So x1 was 2.5, y1 was negative 0.5, and then z1 was negative 3.5. Okay, and then what I called vector v will be x2 is 0.5, y2 is negative 3.5, and z2 will be 2.5. And already, oops, sorry about that, let's show you what I actually calculated. And just looking at that quickly, I think we can see that the magnitude of u is going to be 2.5 squared, plus negative 0.5 squared plus negative 3.5 squared. Okay, and the magnitude of vector v is going to be, what do we have? 0.5 squared plus negative 3.5 squared plus 2.5 squared. And without calculating it, we can see that these two magnitudes are equal. Okay, I did it again. I forgot to show you that bottom part there. Okay, so again, what I just did is I took the magnitudes of the first vector and the second vector, and just by looking at it, I see the 2.5 squared is the same, the 0.5 squareds here are the same, 3.5 squareds are the same, so these magnitudes are equal. Okay, and since opposite sides of a parallelogram are also equal, I don't really have to calculate the other two sides. So we can say, therefore, this is a rhombus. This is a rhombus. Whoops. So we can make that determination. Okay? So we did part one. We showed that it's a rhombus. Now they want us to actually determine the lengths of the sides. Well, this is where now I guess I'm going to have to take my calculator and actually calculate this here. So let's do that as quickly as we can. So what do we have? We have the square root of 2.5 squared plus, and I know that's going to be an addition, so plus 0.5 squared. Okay, and then plus 2.5, sorry, in this case here, I did the first one, so 2.5 squared plus 0.5 squared plus 3.5 squared. Okay, close that off, and what do we get? We get 4.33. Okay, so the magnitude of u, which is equal to the magnitude of v, okay, is approximately equal to 4.33. Okay, for both of them, so no need to find the other two sides. And now let's determine the angle between the sides. Well, let's determine the angle between u and v up here. Okay, and of course, when we have the two vectors in algebraic form, I can find their magnitudes I can use the dot product to determine the angle. Okay, so here we've got u dot v is equal to the magnitude of u times the magnitude of v times cosine of theta. Well, u dot v we can calculate here, so let's do u dot v. So 2.5 times 0.5, so in fact let's just do it directly on the calculator here. Okay, so we multiply the x's, 2.5 times 0.5, and then I add to that the product of the y's since they're both negative. Okay, we've got that, I can just use the positive version, so 0.5 times 3.5, and then here, since it's going to be negative 3.5 times positive 2.5, it's going to be minus 3.5 times 2.5. So the dot product is equal to negative 5.75. Okay, so the left-hand side is negative 5.75, and here, well, we have the magnitude of u times the magnitude of v. They're equal, so 4.33 squared. Cheating a bit with not using the exact value, but we'll leave it for now, times cos theta, and so cos theta is equal to negative 5.75 over 4.33 squared. And so let's go up here. We've got theta is equal to inverse cosine of this, so inverse cosine of negative 5.75 divided by 4.33 squared, and that's equal to 107.86 degrees. So 107.86 degrees. Okay, now when you take a look at this theta value, we notice the way I drew my parallelogram, I drew it on the acute angle side. Okay, it doesn't really matter. Remember that we were just using this diagram to work with the relationships between sides and vectors. Okay, so since this is a parallelogram, what we found would have been the obtuse angle, so that's our theta. Okay, we know this angle here will also be theta, and what we have to find is these two angles, but since they're equal, we know that, and let's call this angle phi. Angle phi will just be, well, the sum of the angles in a quadrilateral is 360, okay, minus, well, we have to take away these two angles here, so 2 times 107.86, and since there's two of them that are sharing the remaining angles, divided by 2, and we have here, so let's do that. Oh, something went wrong. I don't know if you guys saw that, but we've got 360 minus 2 times 107.86, 107.86 equals, and then divided by 2, okay, 72.14. Okay, and there you have it. We have that we've proved that it's a rhombus by showing that all four sides are equal. We found the side lengths for all four sides, and we found the angles. So we have two angles of 107.86 and two angles of 72.14. Okay, that is it.